Good morning, everyone, and welcome to this lecture. This is lecture number 6 in thermodynamics heat, and we are dealing with kinetic theory of gases. In the previous class, we had gone through the various gas laws and we had seen the ideal gas equation. We had solved some really good problems on the ideal gas equation, which I am sure that you would remember, and you might get, if ever there is a problem on ideal gas or ideal gas equation or gas laws, which is possible because these topics are common for both physics and chemistry. So you can get a question. I'm sure that the question would be from this domain that we have discussed, because we have done all types of questions that were possible in this.
Yes.
Today, now we start with the original theory of kinetic theory of gases. Remember, this is a theory. Do you understand the difference between a theory and a law? What is the difference between a theory and a law? Kinetic theory of gases is a theory. Big Bang theory is a theory. Charles theory, Darwin's theories of evolution is a theory. Newton's laws of motion are laws. Gravitational law, Newton's law of gravitation, it's a law. What's the difference between a theory and a law? What's the difference between a theory and a law? Yes, I've given you some examples of some laws and some theories. What is the difference between a theory and a law? Yes, bacha.
No idea, sir.
No idea. It's not a question of physics. It's a general question. Theory and law. Theory is something which someone proposes, and you don't have a proof for it. So that is a theory. It is not proved, but it can explain what we see around us. Wave theory of light, particle theory. It can explain what we see. But if something cannot be proved, it still remains a theory. It does not become a law. A law is something that is experimentally proved. So that is a law. This, my dear friend, is a theory because it explains most of the phenomena that we see of gases, but we have still not been able to prove it experimentally. Therefore, it remains a theory and it does not become a law. That is the difference between a law and a theory. Now, wherever there is a theory, there are some postulates. When I say postulate, what do I mean by a postulate? Postulate means assumptions. Every theory is based on some assumptions that we assume something. So there are some assumptions based on which the theory has been formulated. So first of all, we have to understand what are these assumptions on the basis of which this kinetic theory of gases has been formulated. Assumptions or postulates of kinetic theory of gases. Do you understand what I'm saying?
Yes, sir.
Assumptions or postulates of kinetic theory of gases. So we'll write the heading KTG. Who gave this kinetic theory of gases? Two scientists by the name of Rudolf Clausius. Heard this name, Rudolf Clausius?
Mhm. Yes, sir.
And Maxwell, James Clerk Maxwell.
Maxwell.
These are the two scientists that gave us this kinetic theory of gases. So we'll go through the way the basic postulates. What are the basic postulates of this kinetic theory of gases? So we'll start from the very first thing, and the very yes.
Nothing, sir.
The first basic concept. First, listen to me, then I'll give you time to write. Every gas consists of extremely small particles known as molecules. Very small particles, molecules. The molecules of one gas are same, but the molecules of different gases are different. Do we understand this? Do we understand this?
Yes, sir.
Very simple. Now, these molecules of the gases of one particular gas will be all identical, spherical, rigid, and perfectly elastic point masses. We take them as perfectly elastic point masses. Do we understand this?
Yes, sir.
The size of these molecules is very less compared to the intermolecular distance. What do you mean by intermolecular distance? Intermolecular distance means the distance between the two molecules. Yes or no?
Yes, sir.
Now, since their size is very small, the next thing that you can write, and I'm giving it point wise, the volume of molecules, the actual volume of the molecules is very less compared to the volume of the gas. Do we understand this?
Yes, sir.
Because the size of these molecules is very small, so the actual volume that these molecules occupy is very small, but the volume of the gas is very large. I hope this is making sense. Yes or no?
Yes, sir.
Now, since they are molecules, they will be moving randomly in all possible directions. Yes or no? No, yes. Now,
Yes.
they will not be having same speed, right? They will not be having same speed. So this speed of these molecules may vary from 0 to infinity, very large speed. Some molecules can have very small speed. Some molecules may have very large speed. Yes or no? No, yes. Everything is making sense.
Yes, sir.
Now, there is a speed known as the most probable speed. Now, the most probable speed is the speed with which maximum molecules move. So, this is known as VMP. Most probable speed is the speed with which most of the or the maximum number of molecules are moving. So, there is since they can have from 0 to infinity, they can have any speed, but most of the molecules are moving with one speed. The maximum number of molecules with whatever speed they move, that is known as the most probable speed. Do we understand this? Yes or no? No, yes.
Yes, sir.
I hope everyone is noting down. One
Sir,
more point I can put here. Yes.
sir, is that fourth point correct or needed any corrections?
Fourth point is correct. Volume of the
Volume
molecule.
of gas
Oh, it's very
should
greater
be
I have
the
written. Sorry. It's very small. It should be the reverse. It's very small. Okay.
Yes, sir.
These molecules obey While they are moving, they obey Newton's laws of motion. So now I cannot put any other point. So up till now, can you note down all these points? Yes or no? I'll give you 5 minutes to note it down. Then let's move ahead and look for the other postulates. First, listen to me, then I'll give you time so that you can write it down. Now, these molecules are in random motion. So, what will happen when they are in random motion? They are going to collide
So
with each other. Yes or no?
yes,
These molecules will collide with each other, and they will also collide
container.
with the walls of the container. Because of their collision with the walls of container, they will exert pressure. But whatever happens, whether they collide with themselves or they collide with the walls of the container, the collision are perfectly elastic. Do we remember that perfectly elastic collisions?
Yes, sir.
Okay. These molecules are colliding with the container as well. Because of this collision with the container, we have the pressure, and this is explained in this point. Now, apart from this collision forces, when they are colliding, there is no attractive and there is no repulsive forces between the gas molecules. So basically, we are taking these gas molecules as ideal gases. We are taking these gas molecules as ideal gases, and therefore the potential energy of these gases is taken as zero. Do we understand this, or this has gone above our head? Saying bye
We
bye.
understand, sir.
All the forces, gravitational force and all those are neglected because we have neglected the potential energy. We have neglected the potential energy. There is no gravitational force of interaction between the two molecules. The potential energy is zero.
Yes, sir.
And if the gas is given sufficient time, the gas molecules will get uniformly spread throughout the volume of the container, and therefore the density of the gas will be constant. Do we understand this? Yes or no?
Yes, sir.
Okay, I'll give you 2 minutes now to note down these points. And we can move ahead with the other assumptions. Now, they are randomly, gas molecules are randomly moving in all directions. Remember, so if I find out the mean velocity or mean momentum, remember they are moving in all possible directions. So their mean velocity or mean momentum will become zero. Do we understand why it will become zero? Because all directions they are moving, so in no particular direction they will have any velocity. Do we understand this?
Yes,
So the
sir.
average velocity or average momentum will be zero, but the average square velocity, the square average velocity will not be zero. Do we understand this?
Yes, sir.
Average cube or average 5 is again zero because one velocity is zero, but average square velocity is not zero. That is what you need to understand. Do we understand this?
Yes, sir.
Between two successive collisions, whatever distance it travels is known as the mean free path of the gas molecules. I'll give you a formula for this mean free path as well. One question has come from here. The time taken for this collision is very small, and the time taken to cover mean free path is very large. Time of collision is 10 to the power minus 8. Mean free path is 1. Do we understand this?
Yes, sir.
Okay. Now, as I have told you, if you give sufficient time for a gas, it will get uniformly distributed. So its mean square velocity in x direction will be same as the mean square velocity in y direction, will be same as mean square velocity in z direction. Pressure in the x, pressure in the y, pressure in the z, pressure will be same because it will be same in all directions. Do we understand this?
Yes, sir.
Remember, all these assumptions become valid if we have a large number of gas molecules. All these assumptions become valid. That is the last point. I hope we have taken all these assumptions and we have understood them. Every assumption come after one after the other, starting from what are molecules to what is happening when they are colliding and what is happening with their velocities and momentums. We understand this? Yes or no? No, yes.
Yes,
Give
sir.
you 2 minutes to note down. Now, how do we derive this in basically kinetic theory of gases with taking all these assumptions? What we basically try to derive is to derive a formula for pressure exerted by the gas, and I'm not going to derive it. I'm just going to tell you how this is done. So basically what is done is we take a cube. We take a cube of length L. A cube has 6 sides, a cube of length L. Then we assume that the molecules are colliding, as you can see, with one of the walls of the cube, one of the faces of the cube. In this case, it is colliding with the face ABCD, which is in the YZ plane. And we find out the change in momentum. The momentum only changes along the x-axis. From that change in momentum, what we try to find out, change in momentum divided by time will give you force. From that force, we find out the pressure and we get the formula for pressure exerted by the gas. I'm just going to give you the final formula because we don't have to go into this. We will do 1 or 2 problems where I will try to tell you how this question can come in exam if this question comes on collision. Anyways, we are not concerned about that right now. What we are concerned is the pressure of the gas. Pressure of the gas can be written by this formula: 1 by 3 into total mass M divided by total volume V into something known as VRMS. RMS velocity square. Have you heard this term RMS velocity?
Yes, sir.
So, first of all, we'll try to understand each and every term here. M means the total mass of the gas. Do we understand this?
Yes, sir.
V means total volume of the gas, total volume of the container. Now, what is this VRMS? VRMS is known as the root mean square
Square
velocity.
velocity.
Root mean square velocity. So I remember it in this way. It is the root of mean of square of velocities. It is the root of mean of square of velocity. So basically, you take the velocity of one particle, Vi, you take the velocity of one particle, Vi, you square it, then you take the mean. How do you take the mean? You add all these squares and you divide it by the total number of molecules. Vi is the speed of one molecule. You divide it by the total number of molecules n, and then you take the root of it. Here this n means the total number of molecules or atoms. Do we understand this? Not the total number of moles, total number of molecules. So this is known as the V RMS velocity. The pressure of the gas is written as 1 by 3 m by V. Capital V means with volume V RMS square. Now m by V, as you can understand, is the density rho. Yes or no?
Sir.
So I can write the pressure. First, listen to me, then I will give you time. 1 by 3 rho into V RMS square. Do we understand this? So 3p by rho ka root becomes V RMS. 3p by rho ka root can be written as 3RT by m naught from the ideal gas equation. Yes or no?
Sir.
3 kT by small m. Now remember, whenever I am using m naught means the molecular mass in kgs, obviously. Small m means mass of one molecule. Capital N means number of moles. Now what you have to remember and understand, wherever number of moles or molar mass comes, R will come with the number of moles or molar mass. Wherever you have one molecule, one atom, K will come, and you will see this coming repeatedly in this particular topic. I'll give you 1 minute to note it down. So what we have done, we can just note it down once again. We have seen the RMS velocity, or you can call it as RMS speed. RMS speed is 3p by rho ka under root. That is also 3RT by molecular mass ka under root. That is also equal to 3kT by mass of one molecule ka under root. Now remember, this entire topic is all about remembering the small points and all about remembering the small relation that I am writing. So what is of utmost importance and only thing that is important in this is you remember which thing is what. This is the RMS speed or RMS velocity. We have one more speed which I call it as most probable
Most
speed.
probable. Yes, sir.
To find out most probable, we just, instead of 3, you take
Root
2.
2R 2P by pi r.
This becomes the most probable speed. Now, when I say most probable speed, I mean this is the speed with which the maximum number of molecules move. Do we understand this? This is
Sir.
the speed with which the most number of molecules move. Then we also have one more which is average speed.
Average
Remember,
speed.
not average velocity. Average velocity is 0. Average speed. Do we understand this?
Yes, sir.
Average speed, and that is 8 by pi p by rho. 8 by pi RT by m naught. 8 by pi KT by m. You should not miss What is here? And you can see from here a very important result that RMS speed is greater than the average speed is greater than the most probable speed. Do we understand this, or this has gone above our head? Bye bye, I'm going bye bye.
Sir,
Ah,
we understand, sir.
you can also write it here. I mean, the simplified version. This is 1.73 root over kt by m. Root over 3 is 1.7. Oh, I've written what I've written. Written it wrongly. This is 2. I've written 3. This is 2. I written 3. Okay, so this is not 1.73. Root over 2 is 1.41. Yes or no? 1.41. This is 1.73 root over kt by m. And this gentleman is 1.59 root over kt by m, and hence you see that relation between the three. Do we understand this, or this has gone above what is saying bye bye, bye bye, bye bye? I'm going. Don't worry about me. Bye bye, bye bye. Huh?
Got it, sir.
I'll give you 2 minutes to note it down. Well, this is about the three types of speed. Now, you have seen the relation between the three types of speed. There is one more topic that may not come as such, may be coming in JEE Advanced. There could be a question based on this, that is known as Maxwell's law. Since Maxwell gave this everything, Maxwell's law or distribution of speeds. What is this Maxwell's law? Is the distribution of speed, and he tries to explain what this RMS speed is. See, RMS speed is just a mathematical calculation. When we talk about a gas molecule, when we talk about a gas, as I've already told you, the gas molecules are moving with different speeds. Yes or no? Some molecules are
Yes, sir.
moving very slowly, some are moving very fast. V most probable is the speed with which the maximum number of molecules are moving. The RMS speed is just a mathematical calculation. It does not tell us anything about the speed, the actual speed. Some particles may be moving with this speed. Some particles may be moving greater than this speed. Some particles may be moving less than this speed. Do we understand this?
Yes, sir.
If we draw a graph between the number of molecules moving with a particular speed and the speed, the graph looks like this, and this is a very important graph that you can remember. If I draw a graph between, please remember, listen to me, then I'll give you time. If I draw a graph between the number of molecules at a particular speed, how many molecules are moving at a particular speed, and the speed, the graph looks like this. You can see V most probable, maximum number of molecules are moving with that speed. V average, somewhere in between. VRMS is the lowest among these three. Do we understand this? This is
Yes, sir.
number of molecules which are moving with that speed. Do we understand this?
Yes,
And
sir.
this is the equation that he gave, the relation between dn and dv. This is out of your course. This is absolutely out of your course, but You can just remember it just for the sake of, since I have it, I have found it out. So I'll give you that relation. This is the relation. dn is 4 pi n m by 2 pi ktd. V square e to the power is just an absurd relation which has got nothing to do with the discussion right now, but this is the relation that you actually get. Do we understand this? Do we
Once
understand?
read the statement, sir.
Yes, beta?
Once see that statement, sir.
Which statement, beta?
That
Which statement
the
you can't see?
VRMS gives a
Which
generic.
statement you don't see?
No, sir. Once read that.
Which one, beta?
First one, sir. The VRMS gives
Nothing,
a
I've
trend
already
line.
told you. VRMS is just a mathematical calculation, nothing. You can't see this?
We can see.
Yes, so VRMS is just a mathematical calculation, nothing else. VRMS is just a mathematical calculation and nothing else.
Sir, that last line, sir. Once see that if it is wrong.
Many of the molecules have speed less than VRMS and many may speed greater than VRMS. Yes, that is correct. That is correct. Molecules may have speed more than RMS. So you can see it in the graph, yes or no? Some molecules are having speed more than RMS. Some are having less. The area under this curve, the area under this curve will give you the total number of molecules. Do we understand this?
Yes, sir.
The area under this curve gives you the total number of molecules which is given in this. The total area under this curve will give you the total number of molecules. Do we understand this? So this question may come, they can give you the area and they can ask you what is the total number of molecules. So the area under this curve is given by this integral from 0 to infinity. Do we understand this? This integral from 0 to infinity? This integral from 0 to infinity gives us the area under this curve, and it is nothing but equal to the number of molecules n. Do we understand this, or this has gone above our head saying bye bye, bye bye, bye bye, bye bye? Huh? Now we there, everyone? Do we understand what I'm saying here? This is not relevant, but the other things are relevant. Have you noted this down? Yes or no? Am my voice getting to you? Yes or no? Am I audible? Am I visible? Okay, fine, fine, fine. I thought that I am not able. I'll give you 2 minutes to note this down. Note down the important points. Tell me once you are done. Well, then this point is important. What is the effect of temperature on the velocity distribution? When the temperature rise, the curve will shift towards right and it becomes broader.
Yes, sir.
This is what you need to remember. The curve shifts towards right and it becomes broader. Do we understand this?
Sir.
So just note this down. It will shift toward right. So all the velocities are increasing. Do we understand this?
Sir.
VRMS is increasing, V average is increasing, and V most probable is also increasing. I hope we understand this. Yes or no? No or yes?
Sir.
Okay, I'll give you 2 minutes to note down this. Well, we have seen this in the previous chapter. We had seen the speed of sound in gases. Yes or no? Do we remember? And then we had related speed of sound in gases to the RMS speed of gas molecules. We had also
Yes.
seen the effect of temperature on the speed of sound and the effect of molecular mass and all those things in the speed of sound. Do you remember this?
Yes, sir.
Then comes the next point, VRMS. When whatever I say about VRMS is same for V average and same for V most probable. Is directly proportional to root over T, absolute temperature. Do we understand this?
Yes, sir.
VRMS is inversely proportional to 1 by root over
1
molecular
by
mass
root
of the
over
gas.
mol.
Yes or no? I'm not.
Yes, sir. Yes,
Does it
sir.
depend on the pressure or temperature? No. Does it depend on the pressure? It does not depend on what?
Pressure.
Does not depend on pressure or density. If temperature is constant. Do we understand this, sir? This has gone above our head saying bye bye, sir. I'm going, sir. Forgive me, sir.
Stand, sir.
Give you 2 minutes to note this down. Now, before going any further, let us do one more point, and you will have the entire day to go through all these formulae, and then we can solve numericals. Kinetic energy of gas molecules. Now, there are a very number of questions which come on this kinetic energy of gas molecules. It is a very simple, straightforward concept. Nothing very mesmerizing about it. But you have to understand it so that you don't make a mistake. Kinetic energy of the gas molecules. If I call this kinetic energy as K. Now, if I talk about the entire gas, that will be equal to m into V RMS square, where m is the total mass of the gas. Do we understand this? This is the
Yes, sir.
total kinetic energy of the gas molecules. KT, K total. Do we understand this?
Yes, sir.
Total kinetic energy of all the gas molecules is half m multiplied by V RMS square. Listen to my things very carefully. Do not think about writing. First listen, then write. This is the total kinetic energy of all the gas molecules put together.
Yes, sir.
Now, I can find the kinetic energy per unit volume. So that will become half rho V RMS square. Do we understand this?
Yes, sir.
Okay. So half rho V RMS square. I can also find kinetic energy per mole. This is known as average kinetic energy per mole. N standing for the number of molecules. So this is kinetic energy per mole. Do we understand this? So we'll have to divide this thing by the number of moles. If I put the formula, everything correctly, I will get to this point. It will be 3 by 2 RT. Or I can write the total kinetic energy as 3 by 2 nRT. different ways of writing the same formula. Do we understand this? What you have
Yes,
to
sir.
see is whenever the number of mole comes, R comes together. I can also write this by N. This is total kinetic energy divided by N. So I will call it average kinetic energy per molecule. Do we understand this?
Sir.
So how will I find it out? M by N into V RMS square. If I put the formula correctly, I will land up with this equation 3 by 2 KT. K comes into the picture. Our new friend, Boltzmann constant. And
Yes,
as I
sir.
always told you, what did I tell you? Wherever, okay. So if I have to find out, let me write the last formula. Kinetic energy, I can write total kinetic energy, I can write it as 3 by 2 NKT. 3 by 2 NKT. Now, you can get a variety of questions on this and you might get confused which kinetic energy is asked. Therefore, strict warning, please read the question carefully and see which kinetic energy are they asking. Do we understand this? Yes or
Yes,
no?
sir.
No, yes.
Yes.
This is the same thing written in tabular form. I'll give you 2 minutes to note down this. And I take you back to this original diagram. What we have found out is the RMS velocity of the gas molecule. Sometimes they may ask you the RMS square velocity along any axis. So if they ask you that particular question, be ready because you know the answer. Do you see the answer? RMS square x, RMS square y, both are equal, and this is RMS, the total RMS velocity divided by 3. Do we understand this? Yes or no? Because it is equally distributed, everything is same. Yes or no? No or
Yes.
yes?
Yes, sir.
Similarly, if you take the root of this, you will get the relation between the RMS velocity. RMS velocity along x, RMS velocity along y, RMS velocity along z. They are all equal, and that is VRMS divided by root 3. We understand this? Or this has gone above our head saying bye bye,
Yes,
bye bye, bye bye. Huh? One more thing, please first listen to me. If the total number of molecules are n, Small n is the total number of molecules. Please remember this. Small n is the total number of molecules. Molecules for each wall. How many walls are there? Walls and ceilings, everything. Number of molecules for one wall will be n by 6. Yes or no? There could be a question where they give you total number of molecules. So for one wall, it will be 1 by 6. Yes or no? For every axis, it will be n by 3. Do we understand this? Or this has gone above our head saying bye bye, sir. I'm going, sir. Enough, sir, for today, sir. We'll see you tomorrow. Do you understand this, sir?
yes, sir.
2 minutes, sir, for your answer, sir. Mass of a hydrogen molecule is 3.32 into 10 to the power minus 27. 10 to the power 23 molecules are colliding per second. Remember what is being said in the question. Per second on a wall whose area is 2 centimeters square at an angle of 45 degree to the normal. It could be straight also. They just made it 45 degree just to make the question more interesting. and reflected elastically with a speed of 10 raised to the power 3. So they are colliding with the same speed and they are going back with the same speed. What is the pressure exerted on the wall? I'll give you 2 minutes to think about it. Everyone has understood the question?
Yes, sir.
You have 2 minutes to give me the answer. Do you want me to help?
No, sir, will try.
I'm not worried about the calculation. If I call the mass of one molecule as m, if I call the number of molecules as n per second, remember they are colliding. If I call the area as a, if I call this angle as theta, of it is 45 only, so you can keep it 45. If I call the speed as v, you can give me the answer in terms of n, m, a, theta. Let us take theta as 45 and v. Give me the answer in terms of n, m, a, and v. I'm only concerned with that answer.
Sir, the answer is m into n into v by a in meter square into into cos 45 degrees.
Yes, that is correct. This is the initial momentum. Initial momentum, if you draw like this is m into v, and this is the final momentum, m into v. You have to find out the change in momentum. So how much is the change in momentum? Momentum is only changing along the x-axis, yes or no?
Yes, sir.
So what is the change in momentum? Final momentum vf minus m into vi, and it is only changing along the x-axis, yes or no?
Yes, sir.
So how much you will get? The change in momentum along x-axis will be 2 m v into cos 45, yes or no?
Yes, sir.
That's it. Now the force exerted by this will be the change in momentum. This is the change in momentum of one particle multiplied by the number of particles multiplied by time, yes or no?
Yes, sir.
Multiplied by the number of particles divided by time. But the number of particles are given per unit time, so just multiply this by n. You will get the force 2 m v cos 45. Let me write it as 1 by root 2, yes or no? 1 by root
Yes, sir.
2 multiplied by n. So this becomes root 2 m v n. That is the force exerted. You just divided by the area root 2 m v n by a, and that is the answer, my dear friends, that we were looking at. Do we understand this? Yes or no? No or yes?
Yes, sir.
That's it. That is the answer that we are looking at. We will be doing more questions on RMS speed in the next class. This is just to tell you, if a question comes on collision, this is how you have to tackle that question. RMS speed and the other speeds are left. We'll be doing a lot of questions in the next class, so be prepared, and we'll try to wind up this with the other concepts of degrees of freedom and internal energy and all that. We will try to do it in the next class, that is tomorrow. I think that's a longer class. I think we should be able to wind this up by tomorrow. So take care and may God bless you all. Bye bye.